get the loud announcement out of the way, and then we're live on YouTube.
All right, thank you very much. Welcome everyone to the award session for this conference. So what happened is that basically, the program committee selected among the accepted papers, top 3 rated papers for invitation to the Journal of Cryptology. So the best paper award, the best student paper award, authored by a single student, and then another paper runner-up for invitation to JOC. And so these papers, as award paper, are given the benefit of a longer presentation as a plenary session, even though the rest of the paper will be presented in parallel sessions. So we would like to start by introducing the best paper award. So the program committee of Asiacrypt 2021 is glad to present the best paper award of the conference to Alice Pellet-Mary and Damien Stehlé for their contribution titled on the hardness of the NTRU problem. So we welcome Alice for the presentation. And I will stop sharing for now.
So I hope this is okay for everyone.
Yes, we can hear you now.
And you can hear me, and okay, everything is good. So thank you very much and welcome everyone. So I'm going to present a joint work with Damien Stehlé from INS Lyon on the hardness of the NTRU algorithmic problem. So I'm planning to have this talk quite high level so that everybody can understand. And if you are very familiar with lattice-based crypto and want to have more details, there is more details in the recorded talk on YouTube. So this talk is hopefully understandable by everyone. And so let me start with context of NTRU, because I guess not everyone is familiar with NTRU, or maybe not everyone heard about NTRU before. So NTRU is an algorithmic problem that is based on lattices, and that is believed to be hard to solve even if you have a quantum computer. So you can use it to build post-quantum cryptography. It's one of the characteristics of NTRU is also that it's quite efficient because it uses lattices with structure, so it's usually more efficient than non-structured lattices. It's been used a lot already. So as an example, I'm citing here 3 submissions to the NIST post-quantum standardization process that are based on NTRU and that made it to the 3rd round. So it's a big proportion of this 3rd round submission based on NTRU. And it's also more than, no, not more, it's 25 years old. So it's actually one of the oldest algorithmic problem based on lattices that was used for cryptography. So it's quite old for lattice-based crypto. So that's the context of the NTRU algorithmic problem. And before going any further, I wanted to discuss a bit and compare it a bit with ring LWE, ring learning with error, because maybe even if you have never heard of NTRU, maybe you have heard of ring learning with errors. It's a more famous one, I would say, and it shares a lot of similarities with NTRU. So I've changed the slide, but almost nothing changed on the slide. So ring learning with error and module learning with error, they are both algorithmic problems based on lattices also that are supposed to be post-quantum and that use structured lattices, so they are quite efficient. Same as NTRU, they've been used to construct a lot of things, and in particular, 3 of the submissions to the NIST in the 3rd round are based on module learning with error. So module learning with error is just a generalization of ring learning with error. And so this problem compared to NTRU is a bit more recent. So it's only a bit more than 10 years old. So that's 2 of the most famous algorithmic problem based on lattices, on structured lattices that are used in crypto. And if we try to compare, if you want to construct cryptographic primitive and want to decide which one you use, most of the time you will use the one that is compatible. I mean, the way of writing the problems are different, and maybe one is more suited for some applications than another one. But you may also have other, I mean, maybe both can be used and you want to know which one is best. So they are both efficient. They are both using structured lattices and quite efficient. They are both quite versatile. So they've been used for many constructions. So I cited like submissions to the NIST standardization process. So that's encryption and signature, but you can also do fully homomorphic encryption. The first candidate in distinguishability obfuscators, they used problems similar to NTRU and ring learning with error. So it's been used for many different things. One of the advantages of NTRU is that it's older than ring LWE. So it's been around for more time, and maybe you feel more confident because people have studied it for 25 years instead of 10, 12 years. So it might feel safer. But there is also one advantage of ring LWE, which is that we have some kind of theoretical security guarantees that come in the form of reductions. So what is a reduction? That's going to be the topic of this talk. So in this picture, I am plotting reductions. So the reduction are the arrows. It's between problem, and it says essentially if there is an arrow here between from decision and true to search and true, it says that if you can solve search and true in polynomial time, then you can solve decision and true also in polynomial time. So it's it can be used to give a lower bound on the hardness of a problem, because you can prove that if you can solve your problem, then you can solve also some other problems that are believed to be hard. So it kind of gives you confidence that your problem is indeed hard. So if we look at this picture, the first line is related to ring LWE. And so you can see that for ring LWE, we know a lot of things in terms of reductions. So I'm going to define for decision and true and search and true in a few slides, but in ring LWE, we also have, as usual, decision variant and search variant of the problem. And in the case of ring LWE, we know that they are both equivalent. So if you can solve one, you can solve the other one. And we also know that they are both equivalent to some worst case problem on module lattices. So module lattices are just lattice with some extra structure. And the worst case problem here is just find somehow short vectors in these lattices. So in the case of ring learning with error, we know that all these are essentially the same level of difficulty. If you can solve one, you can solve the other one. And so that's nice, because if you want to do crypto, you are going to use a decision variant of ring LWE. But you know that if someone is able to break this problem in polynomial time, then they will also be able to break a bunch of problems on module lattices that are believed to be hard and that have been studied independently than ring LWE. So now if you look at the NTRU state, we know much less. So the only reduction we know among NTRU problems is that if you can solve the search variant, you can solve the decision variant. So this is not very surprising. Just at a high level, the search variant, it asks to find some secret information related to NTRU. And the decision variant, it asks to distinguish if something is NTRU or uniform. So if you can recover some secret information, usually you can distinguish. So that's almost immediate reduction. And we also have a reduction that shows that decision NTRU is no harder than decision ring LWE. So it's not helpful in having lower bound. It's an upper bound on the hardness of NTRU. It says it cannot be harder than ring LWE, but it doesn't say anything on the lower bound hardness of NTRU. So that was the topic of our article. And what we did is we proved a bunch of reduction for the NTRU algorithmic problem. So it's not as perfect as in the ring LWE case yet, but there are more, we have more knowledge about how decision NTRU relates to search NTRU and relates to some worst case problem on structured lattices. So we had to introduce two search variants. So we splitted the search variant of NTRU to two different variants, which do not seem to be equivalent. At least we don't know how to prove it for the moment. But what we can prove is that there is one of the search variant which is equivalent to the decision variant of NTRU. So this gives some lower bound security guarantee for the decision search NTRU, that if you can solve it, you can also find some secret information related to NTRU. And we proved that the other search variant is at least as hard as some worst case problem, not on module lattices, but on ideal lattices, which are a specific class of module lattices. So specific structure lattices. And maybe let me just comment on this weird arrow with a plus. It means that if you can solve both search NTRU, the first one, search NTRU 1, and the worst case problem on ideal lattices, then you can solve the second variant of search NTRU. So just a small disclaimer here. It's true also for the reductions between ring LWE variants, but so all these reductions, they require some specific range of parameters, and sometimes also some specific distribution over the instances. And so you may not compose all the arrows. So if you want to know if multiple arrows compose, you have to look at the details to know if you can compose them. And yeah, in particular, in our reduction, we use two different distributions for this reduction from search NTRU 1 to decision NTRU, and from the worst case problem to search NTRU 2. So that's the context. And in this talk, I'm going to focus just on this equivalence. If you want to have more details on the other reductions, you can have a look at the YouTube video. And so let me start by defining NTRU now. So I'm going to use a bit of notation depending on whether you are familiar with number fields or polynomial rings or not. You can choose the column you like. So I'm going to work in a ring R, which is usually the ring of polynomials with integer coefficient modulo x to the n plus 1 for n the power of 2. But if you don't like this ring, you can just think of R being the ring of integers, and it doesn't matter for most of the talk. K is going to be the fraction field of R. So polynomials with rational coefficients are just the field of rational numbers. Q is the same in both cases, it's just an integer larger than 2. And RQ is just a notation for R modulo Q. And so I need also a notion of size. So what is the size of an element in the ring R? So if you are in the polynomial case, then you just see your polynomial as a vector of the coefficient of the polynomial. And then the size is the Euclidean norm of this vector. And if you are in the case of integers, then the size is just the absolute value of the integer. And just a small remark that you can also replace the number field here by any other number field you like. And you just need to take the Euclidean norm of the canonical embedding instead of coefficient embedding.
Did we lose audio?
Alice, I believe you've frozen and we've lost your audio and video.
So hopefully she rejoins soon. Oh, she's there.
Alice, we do see you're back, but I think your audio takes a minute to kick in. So just keep trying to talk and I'll let you know when we can hear you. Oh, I say that very confidently and then I can't actually hear you yet. You may want to try without your headphones. Oh.
Can you hear me now?
Yes, but you're very, very quiet.
like, is it better?
Kevin says no, I say vaguely.
Okay.
Thanks everyone for bearing with us. We're apparently having lots of problems today.
Best paper doesn't mean best microphone.
I think you're trying to test audio. We don't hear you at all now. Just... Oh, wait. Yes. Yes, you're still quiet though.
Oh, maybe now better?
Kevin? Oh, who's also muted, but I think he's shaking his head no.
Only slightly.
Yeah, maybe I speak very close to the screen. I don't know what.
Ah, yes. Just
We hear
out
you
of
now.
nowhere that came through.
But this one is good.
Yes.
Yes.
Okay. Okay, sorry. Yeah, for some reason, I don't know.
You're actually too loud now.
Okay. Is it good like this?
Yes.
Yes.
Okay, sorry for that. So I was discussing notations. I hope this is okay for everyone. And so now I'm going to move on to the definition. So what is NTRU? If I define it very briefly, so it's an NTRU instance is an element in the ring R mod Q, which can be written as F over G for some small f and g. So here the division is performed modulo Q. So inversion is mod Q, and f and g small means that there should be much smaller than square root Q, because square root Q is what you would expect if H was uniform mod Q. So you would expect to be able to write it as F over G with f and g of the order of square root Q. And here you have some parameter gamma, which is called the gap. And the larger gamma, the smaller the number of f and g's, and the smaller the number of h that are NTRU instances. And so this small pair of f and g's that can be used to write h as f over g is called a trapdoor for h. And so just a remark here is that the trapdoor is not unique. Usually you have different ways to write h as f over g and f prime over g prime with small f, g, f prime, g prime. But there is something which is unique, which is the one-dimensional subspace spanned by the vector fg. So if you have two trapdoors, then f prime g prime is just alpha f and alpha g. It's on the same line. And another way to write it is that if I perform the division over the rationals, so not modulo q anymore, then this value is unique. And it's what I'm going to call hk. So that's NTRU instances. So the decision variant of NTRU is just distinguish. I give you some element h and I ask you whether it's uniform mod q or whether it's an NTRU instance. So you have some distribution of NTRU instances and you have to distinguish both distributions. So that's a regular definition. For the search variant, so I'm going to define only the first one. And this is the following. So I give you an NTRU instance h and I ask you to recover the element hk. So the unique element in the field k that can be written f over g for any trapdoor f and g. And so maybe you feel this is not very natural definition of search NTRU. Maybe you would like to define search NTRU as recovering f and g. So that's actually the second search variant. But in this talk, I will only focus on this one. And so sometimes I drop the one because that's the only one I'm going to be interested in here. So that's it for the definition. I hope it was clear. Now I want to give you some high-level idea of the reduction. So the reduction is, I want to prove that if I can solve decision NTRU, then I can also solve the search variant of NTRU. So I want to solve search NTRU, so I'm given some NTRU instance h, and I want to recover hk, which is f over g in the fraction field k. And I can use an oracle that solves decision NTRU to help me find this HK. So that's the meaning of the reduction. So here I'm going to assume my oracle is perfect in the sense that if I give it some element H in R mod Q, the oracle is going to say, yes, it's NTRU, if and only if this element H can be written as F over G with F and G smaller than some bound B. So it's perfect in the sense that usually you just know that if F and G are very small, it says yes. If F and G are very large, it says no. And in between, you don't know. So here it's perfect, like there is a B and there is a clear phase shift between smaller than B and larger than B. So what do I do with this oracle? So the idea is quite simple. We just take some elements in the ring, X and Y, and we create a new instance, H prime, which is XH plus Y. So if I write it as a fraction, it's XF plus YG divided by G. And I'm going to query my NTRU decision oracle on this H prime. So now if XF plus YG is smaller than B, the oracle is going to say yes. And if XF plus YG is larger than B, then with high probability, the oracle is going to say no. So by doing that, I can learn whether XF plus YG is small or not. And this is something I can do for any X and Y I choose. And in particular, I can choose X and Y so that they only act on one coordinate of F and G at a time. So I can split the coordinates of F and G and I can come back to a one-dimensional problem. So if you were thinking of everything over Z, it was already one-dimensional, but otherwise, I mean, in all cases, we can go back to something one-dimensional, which I can phrase as, I have two secret elements, F and G, that are real numbers. I can ask any X and Y that are also real number, and I can learn whether XF plus YG is larger than B or not. And my objective is to recover F divided by G. And I'm sure if I give you just 5 minutes to think about this, you will come up with a nice an algorithm to solve it. Let me just give you one algorithm, one easy one that does it. So I'm going to find equation x0f plus y0g is b by just picking some very small x0, y0 so that it's smaller than b and increasing, for instance, y0 until it becomes larger than b. I do that twice, I get 2 equations, and then I can just solve for f over g. So that's if the oracle is perfect. I'm going to skip when the oracle is imperfect, but essentially we just, which is most of the case, but we are just going to use a framework called the Oracle Hidden Center Framework that was introduced by Pierrick and Stefan Davidovits in the context of ring learning with error. So we just need to phrase the problem in this framework, and then we can use their algorithm, and it's going to work. So let me skip this, and let me conclude briefly. So just wanted to mention a bunch of other related works on the hardness of NTRU. So we know in terms of hardness guarantees that if F and G are large, so it's not the context of this talk. In this talk, we wanted F and G smaller than square root Q, but if you take them slightly larger than square root Q, you can actually prove that F over G is statistically close to uniform modulo Q. So it's probably, decision NTRU is probably hard in this context, but you need F and G quite large, larger than square root Q. In terms of attacks, so I've told you that NTRU is a lattice problem, so you can break it using Lattice's algorithm reduction. So this is an upper bound on the hardness of NTRU, right? So if the gap is too large, you can break NTRU using lattice-based reduction. And you also have some specific attacks that target only NTRU and not all lattice-based problem. So in some regime of parameters, it's also broken. So just to conclude, this is a recap of the reduction we proved and a bunch of open problems related to this reduction. So the one I already mentioned is that we are using different distributions for the different reductions. And so it would be nice to have one distribution of NTRU instances that work for all the reductions. Another interesting problem is whether we can prove hardness of search NTRU based on worst case problem on ideal lattices. So this would prove hardness of decision NTRU also based on this worst case problem. And finally, also whether maybe we can replace these problems on ideal lattices by more general problems on modular lattices for modules of rank larger than 2. So that's all for me. Thank you for your attention and sorry for the technical problems.
Okay, so thank you very much, Alice, for your presentation. So do we have any question? I can't see any in the chat. So like if there are short questions in the audience, maybe you can unmute yourself and ask if you don't type it in Zulip. So in principle, we're kind of out of time. So maybe if there are no questions at all, we will let you take these questions offline. But if there is a very short one, we can maybe. Okay, so I can't see any. So okay, so thank you very much, Alice. We'll move on to the second award paper. Let me share my screen again. Okay, so the second award paper is the Best Student Paper Award. So I'll read the blurb. So the Program Committee of Asiacrypt 2021 is glad to present the Best Student Paper Award of the conference to Tim Beyne for his contribution titled Geometric Approach to Linear Cryptanalysis. So Tim, the floor is yours.
Thank you. So thank you. In this presentation, I want to introduce a different approach to linear cryptanalysis. So many of you, even if you're not working in symmetric key cryptography, have probably heard about this technique. So linear cryptanalysis is really one of the most important techniques used to analyze modern block ciphers and cryptographic permutations. So we have a function f here, such as a block cipher with a fixed key. And what we are interested in is linear combinations of the input and linear combinations of the output. So a linear combination of the input is something I can write as a bit vector u transpose times the input bit vector x. And we want to know what the probability is that this linear combination of input bits is equal to that linear combination of output bits. And if this is a cryptographically strong block cipher, then we expect this probability to be very close to 1/2. So we can define a measure of quality of this linear approximation as 2 times the distance of this probability from 1/2. And one sort of well-known fact is that if you have a correlation C, so this quality measure is called the correlation, then with 1/c² samples, you can set up a linear distinguisher with a reasonably good advantage. So this, of course, can be made more precise. And given the central importance of linear cryptanalysis, it's not so surprising that this basic idea has been generalized, has been extended. And I just show a few extensions here on the slide. Maybe you recognize some of them, but it's not a problem if you don't. And what I'm interested in this presentation is the analysis of this function. And I want to understand why a certain approximation has certain correlation, and also how to generalize that to all those variants. So I'm not so interested here in things like the data complexity or the advantage of those distinguishers. So not the statistical aspects, but the theoretical analysis of this function. So I want to just give a brief tour of this new approach, which I call a geometric approach. And I'll do that by going over three goals that it has. And the first goal I want to discuss is that it tries to give a uniform description of all the different input and output properties that are used in all those variants that of linear cryptanalysis that I showed on the previous slide. But before talking about input and output properties, I want to kind of sketch the setting in which this whole theory will take place. And that's the setting of inner product spaces. So we will work in an inner product space consisting of all functions from a set G to the complex numbers. And this set G actually will be a finite abelian group in many cases, but is not essential for most of what I'm going to do today. So this set of functions is a vector space. You can add functions and you can multiply them by complex numbers. And actually, it's just like the prototypical finite dimensional complex vector space, because you can map such a function to a list of evaluations of that function on every element of this set G. And it's not just a vector space, but it's also an inner product space. So there is, between any two functions, you can define an inner product. You can define it in terms of its coordinates like that. So here the overline is a complex conjugate. And that gives this vector space a very clear geometry. So you may remember from high school, if you have two real vectors in the Euclidean plane, then if they make, if the shortest angle, smallest angle between them is theta, then the that's the same as the cosine of theta is then the absolute value of the inner product between those two vectors. And the same thing you could say holds in higher dimensions. And in the complex case, although this angle is a little bit more tricky, you can still give that kind of, or have that kind of geometric intuition. And just one thing I want to mention, just to be clear, is that if the inner product between two functions is 0, then I will say that they are orthogonal. So this means you have two perpendicular vectors here in the figure on the right. So now I can talk about input and output properties, and I'll link that to those inner product spaces soon. So what is an input property? Well, that might be, for example, a set. So typical thing you might do in cryptanalysis is taking values from a certain set. So you have a subset as of the domain of the cipher. And then an output property could be something like counting how often the output is in another set R. And another way of thinking about this whole thing is to say, instead of taking a set as the input property, I can think of the set as an indicator function. So that is just a function which is 0 everywhere and 1 on this set. And this is a real function. It's also a complex function if you want it to be a complex function. And then for the output property, we could say, yeah, that's also an indicator function of a set. But that's not exactly what we want. What we really want is we want to count how often, for a given indicator function, we want to count how often the elements of that set indicated by that function are also in R. So we want a function which maps a function in CG. So this is the set of all those functions from G to C to a number, which is that number of times it's in R. And this function can be defined by just taking the average, or I mean, just the sum actually over the set R of the input function. So that's the same as taking the inner product of the indicator function of R with F. So if we apply that to the indicator function of the output set, I mean, then you indeed get the size of the intersection of R and the output, which is what we want to know. So in a very general terms, and this is the starting point for this geometric approach, you could say that an input property describes a state. So what is a state? It's a collection of values, and for each value assign a weight, and that weight I will take to be a complex number. And then an output property is a way of observing the state. And so that will mean a function from states. So these are functions from G to C to the complex numbers. And I'm going to require this function to be a linear function, because that allows us to evaluate it sample by sample, among other things. But I can simplify this a little bit, because for any function G star, which is, so if you are familiar with, which is a function in the dual vector space, I can just find a function from G to the complex numbers, so that G star of F is the same as taking the inner product between that fixed function G and F. So in other words, both input and output properties could be represented by functions from G to the complex numbers. And then, so one thing we need, of course, is if we have a state F, so a function, how does it change when we apply a block cipher cryptographic permutation? And the relation here is given by a linear transformation. And the only thing that transformation does is, if you have the delta function at x. So this is just a function which is 0 everywhere except when the input is x. Then that should be mapped to delta f of x. And by linearity, that will define this whole linear transformation. And then, so this transformation. This can be represented by a matrix because it's linear. And you could do that with respect to certain bases. So one possible basis is this basis of delta functions. And another possible basis is the basis of group characters. And I don't want to talk about this here too much, but in the video on YouTube, that's a bit longer, I explain it a bit more. The idea is just that we do a change of basis to a more convenient basis. That will be the group character basis. And this is known as the Fourier transformation. And then we get a different linear transform, or we get a different matrix representation of the same linear transformation. And I will call that T superscript F, C superscript F, and that is also known as the correlation matrix of the function F. And this plays a very important role in, let's say, the classical theory of linear cryptanalysis. And the goal of this whole thing is that if you add a key or a constant, then the correlation matrix will be diagonal, which is much easier to work with. So that's why we do that in practice. Now going just a little bit further, input properties and output properties can more generally be described by a subspace of functions. So it's a vector space of functions. That just means that we are considering all the states in that vector space at once. Or for output properties, we are considering sort of the inner products with all the functions from that space at once. And this is needed to describe some important cases such as multiple linear cryptanalysis and also the case of projection functions, which is a kind of general type of input-output property that I discuss in a bit more detail in the longer video. So one thing I just want to mention here is that every result that I'll present in the next slide and that's presented in the paper has to be independent from the choice of the basis for V. It's quite important because it turns out sometimes two different attacks are actually the same when you think about these subspaces, but they're just, they look quite different only because of the choice of the basis. So an example of that would be multidimensional linear cryptanalysis and chi-square, some types of chi-square distinguishers. So now we have a way of describing input and output properties that is the same for all these variants of linear cryptanalysis that I showed on the slide in the beginning, and also some other ones. And based on that, I now want to generalize the notion of a linear approximation. So I can say a linear approximation can be generalized to just something what I will call an approximation. And this is just a pair of two subspaces, U and V, of functions. And U here is, you should think of that as the space of, or the input property space, and V is the output property space. And between those two spaces, I define an approximation map. And the idea behind this map is for a given state in U, after transforming it through a function f, this gives you the vector v that's the best approximation in some sense in V. And this mathematically, it's a composition of three maps. So it's a inclusion map from U to just the whole space, then this transition matrix, and then an orthogonal projection on V. So this kind of contains the information about all the inner products between vectors in TFU and then vectors in V, but it does that in a basis-free way. And just one concept I want to define here is the notion of principal correlations, which are the singular values of that approximation map. So in this figure, to simplify a bit, I assume here that f is an injective function, like a block cipher would be. So we have these two spaces, and the principal correlations are the cosines of the minimal or principal angles between those two spaces. So in the real case, it would look something like this. So here there is a common line. So that's first principal correlation of 1, because the angle is 0. And then there's a second angle, minimal angle between those two planes, which is in the cosine of which is in the principal correlation. And in the case of linear cryptanalysis, so this is explained a bit more in a bit more detail in the video. those principal correlations, or there is only one because U and V are one-dimensional, will then correspond to the absolute value of the ordinary linear correlation that I mentioned in the second slide. So given that definition, there are a few different cases that we can consider. One case is where your space TFU is just contained within V, and that's what I'll call a perfect approximation. So some examples of that are integral attacks, and if U and V are equal, we get invariance, including invariant subspaces and nonlinear invariance. And then you can take the opposite case, where this space TFU is perpendicular to this V. And this is what I will call zero correlation approximations, because among other things, this includes zero correlation linear cryptanalysis. And there's a simple link between those two, because if you flip this plane V by taking the orthogonal complement, then you go from a perfect to a zero correlation approximation. That's a very simple result, but it includes some non-trivial links, such as the link between integral attacks and multidimensional zero correlation linear cryptanalysis. And then, of course, yeah, we have in general, what do we do? So in general, these are kind of probabilistic approximations, and then the quality of this approximation depends on this approximation map. And this includes things like ordinary linear cryptanalysis. So for such a pair of subspaces, an approximation, what we want to do in general is to compute or estimate the approximation map. And for doing that, we will need this idea of trails and piling up. So what are trails in ordinary linear cryptanalysis? So the idea is that typically a block cipher will be composed, so will be a composition of a number of simpler functions. So I call them F1 up to Fr in this slide. And then we assume that for each of those simple functions, it's easy to find masks. So U1, U2, for example, for F1. So that form a linear approximation with a known correlation. And then we want to have a way of gluing together all those one-round approximations into an approximation for this composition of functions. And the big question here is, of course, what is the correlation for this glued together approximation? And the basic principle that's used in the vast majority of linear attacks is known as the piling up principle. And it says that the correlation can be approximated by the product of those one-round correlations. And this product is also called the trail correlation. So the sequence U1 up to UR plus 1 with all these intermediate masks, that's called a trail. And of course, this piling up principle, that's a heuristic. In the longer video, I also show a bit where this is coming from. Basically, there have been two main motivations for that heuristic. The first one is Markov cipher assumption. And I will not say too much about it here. The main problem with this is one, that it assumes that you have independent round keys, which is really not realistic. But much more important, it assumes there is a round key at all, and it assumes that it's random. We are actually in any attack, we are never interested in the average correlations. We are always interested in the fixed key correlations. It's just that sometimes the fixed key correlations are almost all close to that average. But for example, for cryptographic permutations, there's no key, so you cannot use that. So a different way to look at this is the dominant trail hypothesis. This follows from a result that first appeared in a paper about correlation matrices by Johan Damien. And that result says that the correlation of a linear approximation is equal to the sum of all the trail correlations, so for any possible trail. And if one of the terms in that sum, so one trail, has a much larger correlation than the others, then you basically get the piling up principle. So this just assumes that one term is kind of dominant. And this is a much better way of approaching it. But it also has some issues, especially when you look at those extensions and variants of linear cryptanalysis. It doesn't really work there. for example, if you have nonlinear approximations, then there is a bit of a problem. What does it mean to have nonlinear trails? There's not really a unique set of nonlinear trails, or a unique way of representing all the other trails. And another issue with this is clustering, but I will not go into that here. So what is the general piling up principle? So here we want to know the approximation map for a composition of functions. And the piling up principle is then a theorem that says that this approximation map is the composition of the one-round approximation maps plus an error term. And that error term can be computed explicitly. And so this is very similar to the dominant trail hypothesis, because essentially if you're using this dominant term here, so this composition, and it turns out to be wrong, then that just means you need to look at this error term and you will need to expand your trail. So by increasing the dimension of your vector spaces, basically. So that is similar to dominant trail hypothesis, but in addition to that, there is here a different motivation for that result, which is geometric, and which the idea of which is that you have a sequence of successive orthogonal projections. And in the longer video, I go into that a little bit more. And you can also check theorem 5.1 of the paper for a complete explanation. So these are my conclusions. I don't think it's necessary to repeat all of them. I just want to say this is only a brief overview. So there are more concrete results and some applications in the paper. Also all the source code for those applications can be found at the link that's shown here on the slide. And if you have any questions, I guess you can ask them now or email me later on. Thanks a lot for your attention.
Okay, so thank you very much, Tim. So we have a bit of time for questions, if there are any. Again, there don't seem to be any in Zulip. So if someone in the audience has a question, feel free to unmute yourself and ask directly, or type it up somewhere. Okay, so again, I don't see any questions. Maybe to give you some time to think about it, we can keep some time for question at the end of the session. So in the meantime, so let's move on to the next talk. So the final paper of this session is going to be the following. So it was nominated for invitation to the Journal of Cryptology, like the other two papers in the session. So the award says the following. So the Program Committee of Asiacrypt 2021 is glad to nominate for invitation to the Journal of Cryptology Gabrielle et Micheli, Pierrick, Gaudry, and Cécile Pierrot as the authors of one of the 3 top-rated papers of the conference, titled Lattice Enumeration for Tower NFS, a 521-bit discrete logarithm computation. So I think Cécile is giving Gabrielle is giving the talk. Yeah. So let me stop sharing, and Gabrielle, the floor is yours.
All right, are the slides okay?
Yes, they are.
Okay, great. Today I'm going to be presenting some joint work with Pierrick, Gaudry, and Cécile Pierrot, which is about lattice enumeration for the tower number filter algorithm, a 521-bit discrete logarithm computation. So as we all know, cryptography is here to give us some means to secure to communicate, in a secure way, even in the presence of eavesdroppers. And secure protocols, cryptographic secure protocols, rely on some building blocks that are cryptographic primitives, which themselves rely on hopefully hard mathematical problems. And originally, these problems were the two following. We had factorization, integer factorization. We had the computation of discrete logarithms, and more recently, problems related to lattices, like Alice presented just before, or problems related to isogenies, etc. And so in this talk, I will focus on one of these mathematical problems, which is the computation of discrete logarithms. So let me start by reminding what a discrete logarithm is. So the setup is actually quite simple. We are given a finite cyclic group G of some order n and a generator G of the group. And we also consider some element of the group. So usually it's known as a target element H. And so when we talk about the discrete logarithm of H in base G, where G is the generator, this is going to correspond to the element X, so the exponent, such that G to the X is equal to H. And so this definition brings forth the following problem, which is known as the discrete logarithm problem, or DLP for short, where we are given a target element H of the group, and we are asked to find this exponent X. So find X such that G to the X is equal to H. Now, of course, this discrete logarithm problem is a hard problem depending on the group G that is being considered. So it can be easy for some group G, and it can be considered very hard from some other groups G. And so for cryptographic reasons, of course, we want to use a group G such that the discrete logarithm problem is as hard as possible. And so cryptography usually considers prime finite fields of the form FPN, the group of rational points over elliptic curves defined over finite fields, or even genus 2 hyperelliptic curves. So we have a variety of choices. Some are bad choices, not the ones that I've listed, but these ones are used in cryptographic protocols. And so in this presentation, I will focus on a particular case, which is the multiplicative group of finite fields of the form FPN. So why do we care about discrete logarithms in general? Well, many cryptographic protocols are going to use a modular exponentiation in their algorithms where the exponent is going to be a secret. So a modular exponentiation is computing G to the X in a particular group G. And so one can see that, for example, in the Diffie-Hellman key exchange protocol, which is a protocol that is widely deployed, which is known, the public data is going to be elements of a group G. So G, a generator, G to the A, G to the B, and the shared secret key is going to be the quantity G to the AB. And it is quite clear here that if one can solve a discrete logarithm in the group G, in order to recover either A or B from the public data, then it becomes easy to compute the shared secret key. So the Diffie-Hellman key exchange protocol is not the only example where the hardness of the discrete logarithm problem is important. More recently, pairing-based protocols use identity-based encryption or signature schemes or short signature schemes. And these schemes are going to have security properties based on assumptions that would become false if the DLP is broken. So going back to evaluating the hardness of the discrete logarithm problem over finite fields, this is not something which is easy. There are various reasons why it's hard. First of all, there are many different algorithms that solve the discrete logarithm problem over finite fields. And not only are there many algorithms, but also their complexities are going to depend on the relation there exists between the characteristic P of the finite field and the extension degree n. So in order to talk about these complexities, one minute introduce this well-known L notation, which is given by the formula on the slide, which I'm not going to read, but it's the exponential something, etc. This formula uses two parameters, a parameter alpha, which varies between 0 and 1, and a positive constant c. Now, from this L notation, one can see that if the parameter alpha tends to 0, we're going to be talking about polynomial time complexities. If the parameter alpha tends to 1, we can see that the expression tends to some exponential time complexity. And whenever alpha varies between 0 and 1, then we talk about sub-exponential time complexity. And this is the complexity that we're going to be talking about concerning all the algorithms we will talk about in this presentation. So this L notation is not only used to talk about the complexities of these algorithms, but it is also used to define families of finite fields. So in particular, it is going to be used to separate finite fields into 3 areas. So if P is the characteristic of my finite field, and I write P as this L notation with parameters alpha and C, whenever alpha is going to be smaller than 1/3, we're going to be talking about finite fields of small characteristics. When alpha is between 1/3 and 2/3, we talk about finite fields of medium characteristics. And when alpha is greater than 2/3, then we're talking about finite fields of large characteristics. And the interesting aspect of these algorithms is that different algorithms are going to be used in these different areas, and the same algorithm is not necessarily going to have the same complexity depending on the area we're looking at. So as I mentioned, there are a lot of algorithms that solve DLP, and they depend on which families of finite fields we're looking at. So for small characteristics, we have the family of quasi-polynomial time algorithms, which are the most efficient algorithms we have to solve DLP. In medium and large characteristics, the most efficient algorithms we have so far are the number-filled sieve algorithm and its many variants. There are a lot of variants. And we focus in particular on medium and large characteristic finite fields, mostly because these are the finite fields that are used in practice. FP6 is going to be our target finite field, as we will see later. So in this presentation, in our work, we performed a first record computation using one of the variants of the number-filled sieve algorithm, which is called the Tower number-filled sieve algorithm. And before introducing our work and focusing on TNFS, let me just spend a second explaining why do we have to do record computations, apart from the fact that we like record computations and it is fun to do. So for these protocols that are widely deployed, it is of course important to choose the right key size. These are things, obvious things, right? If we're choosing a key size which is too large, we're doing needlessly expensive computations. If we're choosing a key size which is too small, of course, our protocol is insecure. But because the running time of discrete algorithms is so hard to predict, record computation actually gives us very valuable information to order or to assess a key lifetime, the lifetime of a key. And so this is why record computations are highly valuable in order to give some recommendations for key sizes. So we performed a first record computation using the algorithm, which is XTNFS. So T in TNFS stands for Tower number-filled sieve, where we're going to exploit some algebraic structure, and X here stands for extended. And the first thing I want to mention is that when we talk about the extended TNFS, we're considering an extension degree which is composite, meaning that the n in FPN is going to be of the form eta times kappa. Now, why is this important? This is because it highly motivated the reason why we chose this variant to implement. So the reason why we focus on XTNFS is it is a very promising candidate to attack finite fields of medium characteristics. So the table that is presented here on the slide shows the asymptotic complexities of many of the variants of NFS in medium and large characteristics. So all the complexities of these algorithms, as I mentioned before, can be expressed using the L notation. And for all these algorithms, the alpha variable of the L notation is going to be equal to 1/3. So it's the same constant, it's the same alpha value for all these algorithms. On the other hand, the constant C varies a lot depending on the variant we're considering. And one can see from the table that for XTNFS in medium characteristic, this constant C, so the numbers reported here correspond to C, is 48. Whereas if we look at the very first line of the table, which is just a classical NFS, the constant C is 96, so quite higher. Now, why we are motivated, why intuitively can we think that XTNFS will perform well in medium characteristic? Well, this can be seen by looking at the form of the finite field we're looking at. So we're considering FPN, and because N is composite, FPN is equal to FP to the eta times kappa. Now this finite field, can be seen similarly as a finite field F capital P to the kappa, where capital P would be of the same bit size of P to the eta. So basically what I'm doing here, I'm just simply thinking of FPN as a finite field where I have increased the characteristics. So capital P is P to the eta, and I have decreased the extension degree. So from N to kappa. And this intuitively means that looking at XTNFS in medium characteristic can kind of be seen as computing NFS at the second boundary case. So we're getting closer to the large characteristic case, where we can see that the constant becomes 48. So the complexity of NFS kind of like decreases between medium characteristic and the second boundary case. So this was kind of our motivation. We focused on this variant. It had never been implemented before, and it seemed like a very promising candidate. Now, in order to actually implement XTNFS and to perform a record computation, we had to focus on the first step of the algorithm, which is collecting algebraic relations. So why did we have to focus on this step? First of all, collecting relations is often, even in NFS, the most costly step of the algorithm. And in XTNFS, as I will explain just now, this does not happen in dimension 2, as it would happen for NFS, for example, but this relation collection actually happens in higher dimension, which brings forth some difficulties, some problems. So let me focus on the first.
We seem again to have audio problems. So, Gabrielle, we can't hear you anymore.
You may want to turn off your camera. That may help the bandwidth.
Thanks everybody for bearing with us. Clearly we're having a big struggle tonight.
Step of the algorithm. I'm back. I don't know if I should.
Welcome back. You should still be able to share and everything.
Yes, yeah, sorry about that. At least it was quite quick, I think, but all right.
You may want to turn off your camera to save bandwidth.
Yeah, I can do this, yes. Where do I turn off the camera? Wait, sorry. Stop video. Okay. Is that better? I mean, can you at least hear me?
Yes.
Yes,
Okay.
we can.
Great. So going back to TNFS, where we are specifically focusing on the parameters of our record computation. So if you have already seen the number field sieve algorithm, you have probably already seen a diagram such as this one, which is a commutative diagram, which allows us to create these relations. So at the very top of my diagram, I have a polynomial ring Rx, where R in the specific case of TNFS is going to be Z iota quotiented by this polynomial H that I mentioned. Just think of it as a degree 3 polynomial in iota. Now, elements of Rx are then going to be mapped to two intermediate number fields, K1 and K2. These number fields are characterized by two polynomials. In my example, on the left, we have x4 plus 1. On the right, we have a polynomial ax2 plus bx plus c. These polynomials are specifically chosen in order to be optimized for the algorithm, both for the commutativity of the diagram and also in order to produce as many relations as possible. And then the elements are going to be mapped into the very bottom of my diagram, which is my finite field FP6. Now, as I just mentioned, this diagram is commutative, meaning that we have two different paths going through the number field K1 and the number field K2, which are going to bring the elements of the polynomial ring Rx down to my target finite field FP6. Now, let me go into slightly more details in what is exactly a relation in TNFS, which will be useful for me to describe the rest of the enumeration algorithm. Well, elements of Rx at the top of my diagrams are going to be polynomials in iota and x of the form a iota minus b iota x. As I just mentioned before, these elements are mapped to two intermediate number fields. So just looking at the left side for K1, these elements phi, the polynomial phi, is evaluated in the root of x4 plus 1, so alpha 1. So I have a iota minus b iota alpha 1. And now, in these intermediate number fields, one needs to check for something which is called B smoothness. So B is a parameter of the algorithm, and one is going to look at the norm of phi of iota alpha 1, seen as an ideal, and check if that norm decomposes into prime factors that are all smaller than B. If this is the case, then we say that the norm is B smooth. Now, if this is the case on both sides, K1 and K2, so if the element phi evaluated in alpha 1, alpha 2, taking its norm decomposes into these prime factors smaller than B, then these elements are mapped down to the bottom target finite field FP6, and the equality that we have in this finite field corresponds to what we call a relation. So these relations are product of prime ideals, and the factor basis that I actually mentioned in the very beginning is going to be a small set of small elements, where these small elements are prime ideals of small norm. So this is how we create a relation in TNFS, which is actually very similar as to how we create a relation in NFS, with the added algebraic structure coming from the tower of number fields. Now I will focus on how did we actually collect relations. I showed you the general idea, but how do we actually efficiently find enough of these relations, so enough of these equations in FP6? So recall that at the very top of my diagram, the elements that I'm considering are polynomial a iota minus b iota x. And so relation collection actually narrows down to looking for a set of linear polynomials of this form, satisfying the two following conditions. First, we want bounded coefficients, and importantly, we want the norms on both sides to be B-smooth. So more precisely, in the context of our record computation, a iota and b iota are degree 2 polynomials. And so what we're going to be looking for are going to be vectors in Z6. So why do we have 6 coefficients? 3 for the polynomial A and 3 for the polynomial B. So we're going to be looking for these vectors C such that we have bounded coefficients. This means that we're looking for a vector C belonging to a region, which is usually known as a sieving region. And we want these norms to be B-smooth, and meaning that we want the vector C to belong to the intersection of some suitably constructed lattices L, which I will talk about just in a bit. So this is the goal of a collection relation, the first step at least, looking for these vectors C. So we have narrowed down our goal to finding these vectors at the intersection of a space, a sieving space, and a lattice L not yet defined. So what is the dimension of the space S? So the particularity of XTNFS and the record computation that we did is that the dimension here is 6, right? As I mentioned, we have 6 coefficients, 3 for A, 3 for B. This is quite different from previous work. If we look at the classical NFS algorithm, for example, sieving will happen in dimension 2, because we are looking for pair AB, where AB are integers, whereas we are considering polynomials A iota, B iota. And to efficiently sieve in dimension 2 for NFS, we have an algorithm from Franco and Klein, which efficiently does that. Now, in the context of NFS, though the classical NFS, it is also possible to sieve in higher dimension. And some work in that direction was done by Laurent-Rémy and more recently by McGuire and Robinson. And in all of these algorithms, so for dimension 2 and for higher dimensions, these algorithms consider as a sieving area a D rectangle, whereas it is just a rectangle or a cube in dimension 3, for example. And so in our work, again, we differ from that in the sense that we are not going to look at a D rectangle, but we are going to consider a 6-dimensional sphere. So we are considering the L2 norm instead of considering the L1 norm. So my area S here is going to be the 6-dimensional sphere. Now, the other side of what I'm looking for is this lattice L. So concretely, what does this lattice L represent? Well, L is a lattice that is going to describe the divisibility of some ideals by first an ideal Q, which is known as a special Q ideal. This is important for the algorithm, but not so much important here, and a prime ideal P in the intermediate number field. And so what is going to be the output of enumeration? So a vector C that is going to belong to S intersect L is going to be a vector that is going to correspond to an AB pair, AB being polynomials, whose norms are going to be divisible by the norm of the special ideal Q and the norm of P. So these lattices L are constructed such that the output elements of these lattices are indeed elements divisible by the norm of the prime ideal P. Now, I talked about intersection of suitably constructed lattices L, so not just a single lattice, but many lattices, because of course, for each lattice, we have a prime ideal P, and we want to find vectors in the intersection for many, many different prime ideals. Why is that? Because if we are divisible by many norms of prime ideals, then we have a higher probability of being B-smooth. recalling that being B smooth means that the norm of my ideal decomposes into factors that are all smaller than B. So we want to find vectors that are at the intersection of a lattice and a sphere. And of course, we looked into the lattice world to find efficient algorithms to do that. And we focus on Schnorr-Oeschner's enumeration algorithm, which is from the 90s. So the input of Schnorr-Oeschner's enumeration algorithm is a lattice basis, and its output is the shortest non-zero lattice vector, the non-zero lattice vector. And the idea of Schnorr-Oeschner's enumeration algorithm, very briefly here, is to construct an enumeration tree, considering different projections of the lattice for each level of the tree. And then at each level of the tree, it enumerates in an interval. And then in order to find the shortest non-zero lattice vector, there's a depth first search in the tree that is done at the end of the algorithm. Now, in our case, the setup is slightly different. First of all, the input. Well, the input is still a lattice basis. In our particular case, we're considering lattices of dimension 6, so ridiculously small compared to what is considered in the lattice space world. And the output is also a bit different. We don't care about the shortest non-zero vector of the lattice. We care about all of the vectors C, such that the norm of C is smaller than R. And R here is the radius of our 6-dimensional sphere. So recall, we want the intersection of L and our sphere. But the idea is very similar. We we did not modify Schnorr-Oeschner's enumeration algorithm by a lot. So we also construct an enumeration tree, consider projections of the lattice, and then we exhaustively search for all the coefficients Vi such that the vector C will have norm smaller than R. So apart from our output condition, the algorithm is essentially Schnorr-Oeschner's enumeration algorithm. Now, as I mentioned, we modified it slightly because we do not want the shortest vector. And also we were able to optimize the computation of the vector C by reducing the number of computations. So we kept a common part which was not for which the computation was not repeated throughout the algorithm. So this seems like a very small optimization. It's a trivial optimization in the code, but because enumeration in TNFS is done many times, this small optimization actually gave us a 10% improvement in our total sieving time, which is really not negligible. So now let us take a step back and look at relation collection altogether, because actually enumeration is just kind of the first step of this relation collection. So first we start with sieving, which in our case, in our particular case, is enumeration. So we have all these pair AB, and we find AB pairs at the intersection of our sphere and many lattices LP. Now this gives us potential relations, meaning we have AB pair with a high probability of being B smooth, but we have not yet tested for B smoothness. We just have potential candidates. Now these potential candidates, which we usually call survivors, are given as input to algorithms which are actually going to test B smoothness for these survivors, for these candidates. But because these algorithms are usually quite expensive, such as batch or ECM algorithms, then we want to use them on a smaller subset. We don't use these algorithms on the entire AB set before enumeration. And now the output of batch and ECM are going to be doubly B smooth elements, which are going to correspond to the relations we were looking for. Now, this is an overview of the entire relation collection. There are some things that I am not going to talk in this talk because it's we do not have enough time. But one important thing that we had to consider is the identification and the removal of duplicate relations. So duplicate relations are going to correspond to AB pairs that are going to basically provide the same information. So it is pointless to keep two of these AB pairs because they do not provide any extra information. And identifying and remove them is something that was actually quite new for TNFS. Duplicate relations exist in the setup of NFS, but because, again, of the added algebraic structure in TNFS, we had to deal with new forms of duplicates, and all the mathematical details are in the paper. So now, we've worked a lot on this enumeration algorithm, on the whole relation collection process. So what did we need what did we need for a record computation? So to kind of summarize a bit where we're at, we focused on a fast sieving algorithm in dimension higher than 2. So in particular, in our work, we're looking at dimension 6. Then we had to identify and remove duplicate relations, as I just explained. There are some other aspects of NFS which had to be adapted to the tower setup. So in particular, adapting Shirakawa maps. This is a particular element of NFS algorithms, which also occur in TNFS, but in a slightly different way. And then we had to glue ourselves to CADO NFS. So CADO NFS is an existing code that is used for NFS record computations. And so all the parts of TNFS, which are basically identical to NFS computations, I'm thinking of the part that I have not talked about, like linear algebra, for example, or the descent, we did not code ourselves. We branched ourselves to pre-existing code, so CADO NFS. And we chose a nice target. So as I mentioned in the very beginning here, we considered FP6. And now this allowed us to perform a 521-bit record computation. So kind of situating our finite field in this small, medium, large characteristics, we are in that close to our second boundary case, where we chose a prime of 87 bits. Now our total computation took a little less than 25,000 core hours. And one can see that the relation collection phase on the little table clearly is the longest of the different steps of the TNFS algorithm. So we're a little over 23,000 core hours for the relation collection. The other steps are a lot less. And we were also able to compare our enumeration or our sieving time, our relation collection time, with other algorithms that also sieved in higher dimensions. So in particular, as I mentioned, there was the work of Maguire and Robinson, and also the work of Laurent-Grémy, the algorithm of Laurent-Grémy. So they focused on the NFS algorithm, so not exactly the same, not the same variant as ours. And they also considered fields that are much smaller than ours. So 422, 423, whereas we chose a finite field of the size 421. They sieved in dimension 3 for their computations, whereas we sieved in dimension 6. But regardless of the fact that we are sieving in a much higher dimension, our sieving time is significantly smaller than theirs. So 23,000 as opposed to 70,000 and 201,000. So this, we were very pleasantly surprised about this. And this kind of comforted us in the choice of especially the sieving area, which differs a lot from their choice. So choosing a sphere, considering the L2 norm instead of the L1 norm. And so I should probably finish by showing you our results. So the actual discrete logarithm. So again, we took a finite field FP6, a prime of 87 bits. I'm skipping a lot of mathematical details here, but you can see our target element, which we chose, can probably recognize the digits of pi, and then running the whole algorithm. So not only the relation collection, but then there's also a linear algebra step and a descent step, allows us to output the log of our target. So this beautiful number. And so thank you for your attention. And this is all for my talk.
Okay, so thank you very much, Gabrielle. So we have a question already in Zulip by Aurore Givik. So yeah. Maybe Aurore, you want to unmute yourself and ask it directly? That would be great. No, if it maybe you don't have a mic or something.
Yes, do you hear me?
Yeah.
Yes, we hear you.
Okay, yes, thank you for your talk and this great result. So my question is about how does it scale for larger prime P, and actually some cryptographer is interested in knowing which size of P is required to get 128 bits of security in FP6. And the second side is how does it scale for other embedding degrees, like your implementation works for FP6. What about FP4 and FP12?
Yes, so for scaling to larger P, so this is actually ongoing work with Pierrick and Cécile. So we're currently looking at a bigger finite field of the size 708 bits. And so, the choice of a 521-bit finite field was a little conservative in the sense that because we were trying a new algorithm, we did not want the whole record computation to take many, many months, which is the case, for example, for the highest NFS record computations for factoring and discrete log. So we purposely chose a finite field where we imagine that our record computation would finish in a reasonable time. So if there was a bug in the code, we could more easily fix it. But we are working on larger characteristic P. And the difficulty, of course, is that sieving, this also kind of goes to your question with a different extension degree. We can sieve in higher dimensions or in smaller dimension if the extension degree is 4, for example. We have to see how our algorithm scales. We are hoping that if we sieve in dimension 8, for example, so from 6 to 8, which is what we are doing for our new record computation, the enumeration still seems to be reasonable, but we will see once the record is done. I guess it is a little uncertain to see if we are starting to sieve in much higher dimensions, if the enumeration algorithm still is sufficiently good to actually allow for record computations in a reasonable time. Was there another part of the question that I didn't answer?
No, thank you. So new records are on the way. Thank you.
I have a question.
Yes.
Go on, Kevin.
Do these sieving techniques lend themselves to other CPU architectures such as GPUs?
Oh, wow. That is not a question I seem to be able to answer.
Because if you're going to scale up to a really, really large calculation, you might give yourself the flexibility to have, special purpose hardware.
Of course, yes.
And somewhere in between there, GPUs are, being used in large quantities for machine learning. And so there's a lot of CPU availability there.
Yeah. No, yeah, for sure. I would think that I want to say the answer is yes, that we could adapt, but I'm not too sure. Not so much an expert in architecture, so yeah.
Okay.
But it would be great. I mean, of course, we need more computational power to have bigger records. So.
Thank you.
All right. So if there are no more questions, either for Gabrielle or for one of the other speakers, I suggest we close this session since we're a little bit over time, although it's understandable given the technical difficulties we met. I'd
like to just make a comment.
Yeah.
In this conference, we have parallel sessions. So we will not be streaming the parallel sessions on YouTube. They will be in the separate Zoom rooms. You can switch back and forth between them, but we'll have 2 separate Zoom rooms open.
And we will be recording the parallel sessions, so those videos will be available sometime after the conference, but they just won't be available during the conference for streaming watching.
Right. So please pay attention. So the regular session will start in a little bit less than about a bit more than 20 minutes. And there are 2 parallel sessions, so you have to choose which one to attend. So again, congratulations to the award winners, and see you in the next session in 20 minutes.